I'll write it down. Now we're going to talk about limits. Okay, thank you. So just to remind you, what we've talked in the first two lectures were about the power of local algorithms and methods. And especially in the second part, hopefully I convinced you that using just in certain algorithmic questions, such as counting matchings, making decisions, making inference based on local information of the graph was already powerful enough to design a good algorithm. Just to remind you, at a high level, what was the picture? The picture was that, okay, we wanted to count the number of matchings in the graph. We've reduced the problem to computing the likelihood that a given node in the graph is a part of the randomly chosen matching. That was an equivalent problem. We've convinced ourselves to that. And then we've discovered that by using some kind of a contraction argument, that essentially the probability that the node does or does not belong to randomly chosen matching in the entire graph is almost the same as the same probability in a small neighborhood around it. We didn't discuss it in the context of neighborhood. We discussed it in terms of this kind of a branching program. But because we stopped this branching program in a small depth, that's essentially like looking at the local information. So that was the first two lectures. We talked about power, but today I want to talk about the limits of local algorithms. And now, if you want to study the power of or limits of local algorithms for arbitrary graphs, that's space of all graphs is kind of too broad to even make any kind of interesting statement. Because think about the problem of finding the largest independent set in arbitrary graph, just using local information versus global information. If the graph is bipartite, then global information is very useful. You know, you need to take the largest part of the two, and that's at least that's the independent set. So you have an independent set at least as large. But if you're only looking locally in your graph, you might never even figure out that the graph is bipartite, and therefore you will produce something which is substantially smaller. But we will limit ourselves to scope of graphs which are random, and we will look at two widely studied graphs, random graphs, models of random graphs, which are just the Erdős-Rényi graph and the random irregular graphs. And in both cases, I'm interested when d is small. So it's order 1, bounded degree or bounded average degree. This is the scope of graphs. On this graph, I'm going back to the maximum. I'm going back to the independent set model. Although the type questions that we will consider, you can ask for any kind of reasonable combinatorial optimization problem. But for the illustration purposes, and so that we can go drill deep into techniques, we'll talk about the independent set model. And now the goal is, instead of counting independent sets in a graph, we want to find maximum independent set. Now, in the context of random graphs, the question of a maximum independent set actually comes in two flavors. So the largest independent set, or a largest independent set, is I star in the graph, and this is the cardinality. Okay, you can ask two questions. First, what is the size of this? For example, what's the expected size of the largest independent set? That question by itself is not algorithmic. That's a structural question, right? What is the true value of this? That expectation has some value, which depends somehow on the model and the parameter of the graph. And then the second question, which is tightly related, is what is the best algorithm? What is the largest independent set that you can produce by an algorithm? And as always, we're interested in polynomial time algorithms. But it turns out that in the context of these graphs, pretty much the only non-trivial class of algorithms that we can analyze are the local algorithms, or their flavors, and I'll give a more formal definition later on. And then, again, the question is, again, can we achieve the best algorithmic bound by local algorithms? What can we do, and so on. So generically, the question is, what is the truth, and how close we can get to the truth. So before I talk about limits, let me tell you, let me give an example of a non-trivial, fairly non-trivial result on the Erdős-Rényi graph regarding defining the largest independent set. Let me first describe an algorithm. So here's a fairly simple algorithm for independent set. What you do is that you start from leaves. So suppose you have a parent, you have 3 leaves with a parent. What you do is that take leaves in. So in the first step, include all the leaves into your independent set. And then, because you've included all of them in the independent set, then the neighbors are out. So I include all of these are in, the neighbors are out, and then repeat. Here's an observation. When you do that, this procedure is never suboptimal, in the sense that you can produce a largest independent set by starting something like this, and in the end, if you run out of leaves, you optimize in the remaining part of the graph. But at least as far as doing these steps, you never made a mistake. And the reason is that if you had an largest independent set, which for some reason included the parent, but did not include the leaf, then you can swap. And instead include the leaf and kill the parent. It gives you the same cardinality independent set, so you never lose. There is a caveat here. There's one place where this actually logic doesn't quite apply. Any ideas? Okay, it's not going to torture you. If you have 2 vertices, if you have an isolated edge, right? Because then you say both of them are leaves, and you have to. But let's say in this case you just take one of them, and that requires sort of a separate analysis. I'm not going to give you an analysis anyway. But short of this situation, this never leads to a mistake. Well, here's the theorem. That's by Karp and Zipser, and it's 1980, and as always, I think it's 82, question mark, around 81 and 82, who proved that if you have an Erdős-Rényi graph, and the degree is less than or equal to e, the number e, then this algorithm, when you run it all the way until you have to stop, and you have to stop when you run out of leaves, what's left over is little o of n. So by this procedure, you exhaust the entire graph, almost the entire graph. And because the largest independent set in this graph, with degree being bounded average degree is order n, that means you've constructed approximately largest independent set. Yes? So the leftover is with high probability, but the independent set that yeah, leftover is with high probability. Yes. What's the size of the? So if you define the core, which is whatever left in this procedure, and the core, which is the min degree 2 graph, that's the one has or little o of n. The core of the graph is larger than this, but the core formally, there is a formal definition of the core of the graph, which is degree 2 subgraph of the graph. It's order n. It's not because you're above a giant component, so it's a non-trivial graph. You are above the giant component regime, but nevertheless, you are actually successful as long as the degree is less than e. And furthermore, when you analyze this, you can also show that if you do this procedure where you put the leaves in and kill the parents, if you do it only t steps where t is large constant, but constant, what you get, the independent set that you get from this procedure is pretty close to the largest, meaning that the difference is something which is controlled by t, something maybe 1 over t or of that nature. So, or formally for every epsilon there exists a large enough t such that the ratio of this to this is at most 1 plus epsilon. So by doing this procedure constantly many times, you can get almost the largest independent set. And I wanted to make this connection because now I want to introduce the general framework of local algorithms. And this algorithm will be a local algorithm provided that t is constant. That's why I wanted to make this connection. But any questions about what I have told you thus far? Okay. So here's the framework of local algorithms. That we will focus on. That is called IID factors. Now, if I'm not mistaken, the discussion of the graph limits that you've heard so far was about dense graphs, not sparse graphs. And so therefore, I assume that you have not seen this concept, except for some couple of problems on the homework assignment. But just to be self-contained, I will redefine it. I'll redefine it again. The concept of IID factors comes up in several branches of mathematics, including graph limits, but I will not discuss that connection. We will just treat it as a very convenient framework of formalizing the notion of local algorithms. So let's define it. So the local algorithms are parameterized by functions acting on bounded depth trees with nodes weighted with nodes weighted. To be specific, consider an arbitrary tree. I'm gonna bound the depth of this tree by, okay, I use t as steps here, and so now for the depth of the tree I will use parameter r. So this is a tree has depth r, And suppose you equip the nodes of this tree with some values u1, u2, u3, u4, and so on. And all the values, we assume that they are in the interval between 0 and 1. So that gives you a weighted tree. Suppose you have a function and which maps this, and I'll write it informally, but because writing this whole thing formally, it's a bit of a mess. It maps a weighted tree, any such weighted tree, into value 0 or 1. Right? Suppose you have this, and this function is essentially acts on infinite space, because first the number of trees in principle could be infinite, but also the number of realization of weights, and I'm allowing real valued weights here, is also infinite. But nevertheless, so we have some function which maps every such weighted tree into decision 0 or 1. Okay? Are these trees rooted? Yes. Although it's not clear what's the role of the root is so far, but it will be clear now. What I want this rule to be, I want this rule to be isomorphism invariant. And that's, I think, where I need a notion of the root. So what it means, something like this. Let's say I have a rule f which acts on trees of depth 1, and this is the root. If I have, for example, 1.3 value here and 0.5 and 0.7, and somehow that maps this whole tree into decision 1, I want the same outcome if I swap 0.5 and 0.7. So the fact that 0.5 is on the left and 0.7 is on the right should be irrelevant. So that means that my rule is isomorphism invariant, okay? And for that I need this really to identify the root. Suppose we have such a rule, then what we can do is we can, I'm sorry? Take care of, in the isomorphism, yes. So if what I'm saying is that if based on this configuration, the output of the rule is 1, then based on this configuration, the output is also 1. But if the weight here happens to be 0.4, then it's completely different. Could be completely different. Could be 0. So is that definition clear? Okay, so the weights are important. So now, what we can do is we can apply this rule, apply it locally on any of these graph models, random Erdős-Renyi graph or random irregular graph, and this is how we're going to apply it. So we're going to generate weights u1, un, iid, uniformly at random from 0, 1, and attach them to nodes. All the nodes of the graph. So my entire graph now, every node has its own weight. Okay? And now I apply locally on this graph simultaneously on all nodes with respect to depth R neighborhood of these nodes. What does this mean? For every node, I look at the neighborhood of this node Now I'm using the fact that this is an Erdős-Renyi graph. So with high probability, that neighborhood is going to be a tree. And that's a fact from Erdős-Renyi theory. And if it's not a tree, we would just declare it to be a garbage, irrelevant garbage that we don't really worry about too much. And it's indeed, because it happens rarely, it's a small order effect, no worries there. So it's a tree, but because every node is equipped with a weight, now it's a weighted tree. So with respect to this being the root of this tree, we have that guy sees the weighted tree, then it applies the rule F, and there is an output, either 0 or 1. And that output is associated with this node. But then we do the same thing for this node, and this node, and this node, and this node, and all the nodes. So what it means in the end, what it means is that we have a mapping that maps any realization of the random weights, into an element of a binary cube. So it maps it into some string sigma, which is part of the binary cube. I'm sorry, can you speak louder? You didn't get. I do it for all the nodes, except for those nodes where, if the node is one of those few nodes where the neighborhood is not a tree, let's say we put it equal to 0, just by default. And it turns out, I just don't want to carry this kind of a garbage, but it turns out that that doesn't change significantly what I need. Any other questions? So what I have described so far is just a simple mapping from IID uniform random weights into 0-1 strings, or basically assigning every node with a 0, either 0 or 1, vis-a-vis some local rule. Now that's a local algorithm, in a sense that that F encodes an algorithm for producing answers. So for example, you could try to design F to produce something good, like independent set, perhaps a large independent set. When you apply such a rule, and you hope to get an independent set, even a large independent set, first you want to make sure that it's an independent set. So you want to make sure somehow that you don't create conflicts. You don't create two nodes which are shared by an edge and both have value 1. And the fact that you can do that in some sort of non-trivial-ish way is the essence of your exercise that you've seen. That at least using this rule, you can indeed produce sets which are independent and have expectation n over d plus 1. Now, I will assume that you already did this exercise, so I'll just repeat the idea. The idea is very simple. You apply the following rule. For every node, you look at its own value and the value of the neighbors. And if the weight of the root is if the weight of the node is largest among its neighbors, then you put the value 1. Otherwise, you put the value 0. So this is 0.8, this is 0.3, 0.4, and 0.6. Then you say 1. Otherwise, you put 0. And then the likelihood that you happen to be the majority among all of your neighbors is 1 over d plus 1, and therefore the likelihood of seeing 1 is 1 over d plus 1, and you never create conflicts because if you have two nodes shared by an edge, only one of them is larger than the other, so conflict is never created. Okay, so we have a reasonable size independent set, and that can be produced by this mechanism. But look at the Karp-Zipser algorithm. So look at the Karp-Zipser algorithm that you run in t steps where t is constant. That algorithm is also a local algorithm, right? Because because the algorithm works until you create a core, and you have to say something until t steps, and then you have to say something what you do after this t steps. Let's say that after t steps of this algorithm, you just declare everybody to be 0. And whatever independent set you created in the first t steps, you declare to be the independent set. Then it's a local algorithm, because for every node, what is its fate? What can happen with this node? Either it was put in because at some stage of this algorithm, or it was killed because it was neighbor of somebody who was put in, or it was left over from t steps. But that's something that depends on the depth t radius of this depth t neighborhood of this node. So just to give you an example, let's say your graph looks something like, neighborhood looks something like this. So you have three edges here, and you have one subtree which goes all the way to the rest of the graph, and another part which goes to the rest of the graph. And then you have, let's see if that works. So you put these two nodes in, you kill this neighbor, you put this in, you kill this neighbor. It's not a good example. So I need something. Okay, here's an example. Suppose you have each of this. Suppose you have something like this. Okay, it's a simple enough example. So you have you have two neighbors. Each of them has one leaf attached to it, and then you have the rest of the tree that then connects to the rest of the graph, and then it's more complicated. Okay. So what's going to happen is that in the first stage you're going to include these two nodes. So these two nodes are in. Then you kill these two nodes, and this node is in. In 3 steps, you figured out that this node is in, even though it's still connected to the rest of the graph, but that was sufficient. All right, so you can do something nice with local algorithms, but now I'm going to switch gears to talk about limits of local algorithms, how far you can go, how far you can push this method. And I'll leave. So to gauge the true power of algorithms, local algorithms helps to know where's the truth. So specifically, if you take a largest independent set in a random graph, I star, take its cardinality, what is the size? What is the size? Theorem. If you normalize the size, and in the interest of time and not to lose the momentum, I'll skip the references and tell you at the end what are the corresponding references. Just want to sort of tell you the story. if you look at the limits, if you normalize the size of the independent set by the number of nodes, and that's the right normalization, that limit exists. This is in the context of, this applies to both random and random deregular graphs. So theorem is true in both cases and actually is the same result. So the limiting ratio exists, and that's called the independence ratio. And that independent ratio, while we don't have a good handle on this number itself, that ratio is asymptotically 2 log d over d as d increases. Okay. So when d is equal to e, then there's some number and it's nothing like this. But when d becomes large, then it's approximately 2 log d over d. Doubly asymptotic result. I want to give you a sense of why this is the case. So let's actually prove an upper bound of this. So we're going to drill deeper, get technical. So let's actually prove of the upper bound. And the way we're going to do that is application of so-called first moment method. And what it means is that we're going to look at let Zm be the number of independent sets of size m. Then the probability that there exists an independent set of size at least m is by Markov bound is at most expected value of Zm. My goal is to show that if the independence ratio is larger than this quantity, then this probability goes to 0. And I will do that by upper bounding it by expectation, and I'll still show that the expectation goes to 0. So I want to oh wait, probability that so that's not what I wanted to say. Probability that exists independent set such that its size is at least m. Good. Good. So I'm ready. So now what we're going to do is that we're going to let m equal to, and we sort of carefully guess the right okay, let m be x times n, and we're going to compute the expected number of independent sets of size x times n. And we're going to see that, well, how large can x be so that this quantity is still, so this quantity does not go to 0. And the claim is that if x is bigger than 2 plus epsilon log d over d, and d is large, then expected value of zx m n converges to 0. In fact, converges to 0 exponentially fast, but that's kind of a nice icing on the cake, but not that important. So we're going to show that expected number, just expected number of independent sets of size larger than what claimed goes to 0. And that will prove that with high probability, the largest independent set is asymptotically only log d over d. And that's the easier part of the proof. That's why I want to do that. So how we're going to do that, the expected number of the independent sets is just the sum of the probability that a particular subset I of the set of nodes is an independent set where you run over all subsets of the set of nodes which have cardinality x times n. Right? So I'm going exhaustively through all subsets of my graph, and I'm putting the probability that it happens to be an independent set by homogeneity. That quantity is the same for all subsets because of the Shreni graph. So this is simply n choose xn, the number of ways to choose the subset, and the probability that one of such subsets is an independent set. Stop me if something is not clear or something is wrong in notation. And so we just need to compute that probability, which is fairly easy to do in the Erdős-Shreni case. Random regular graphs, it's more involved, and we're not going to do that. But Erdős-Shreni case, it's easy. So let's continue. It's n choose xn. Here's your graph. Here's your subset I. The likelihood that this subset is an independent set is simply likelihood that all the edges, internal edges, are missing. And that probability is the probability of not having an edge in a concrete location times, let me push this a little bit here, I xn, times the number of internal edges, potential internal edges, which is xn minus 1 over 2. Remember that the size here is xn. Yeah? Any questions? So now we're going to just work on this, and now it becomes a pretty common race of asymptotics. We have one term which grows exponentially in n, and we have another term which decays exponentially in n. Well, because you have something over 1 minus constant over n to the power n squared. So we're going to simplify it a bit now and compare exponents. The first exponent we will write, so n choose xn, and I'm going to repeat it here, you can write it as exponent n x log x plus n 1 minus x log 1 minus x. It's just the usual entropy term. That's for combinatorially explosive part. And the second asymptotics you can write as exponent. Well, it's 1 minus d over n to this exponent, so it's up to the order n, it's minus n x d x squared over 2. And then there's a little term here, which is order little of n, and the little of n term here, that will be irrelevant. Okay, so it's just an algebra. I hope you're fine with that. So therefore, the asymptotic terms are, let's just sort out the asymptotic term, x log x, 1 minus x log 1 minus x. And nobody corrected me that I'm missing a minus sign here. I'm missing a minus sign here. So it's minus this, minus n times this, minus n times this. The way to check it is the log of some number less than 1, so log of that number is negative. It should be going to infinity, so it's minus here. And here it's fine, it's a term going to minus infinity. It's a d x squared over 2. Okay, so now the question is how large I can make x so that this exponent is still positive, or at what threshold it turns negative. Once it turns negative, that quantity is negative, and this expression goes to 0 exponentially fast. Yep? Thank you. All right? So you could, for fixed d, you could optimize it, but this optimization problem doesn't give you anything explicit. We're going to use the fact that d goes to infinity. So, in which case it actually simplifies, and indeed we can get a somewhat of a nicer expression. So, sort of, let's do the following substitution in sort of with the power of foresight. Rewrite x as log d, t times log d over d. I'm sort of suggesting that the right answer for x will be of the scaling log d over d times some constant, and we need to figure out that constant. Okay? Okay, so let's fine. That's in any case a valid substitution, and let's put it in. So you have minus x, which is t log d over d. Now, from this point on, it's just a fairly simple algebra, but why not do simple algebra when it's already end of the workshop? Okay, so t log d over d times the logarithm of this. Now, what is the logarithm of x? So we have a minus sign here, minus log d plus log d plus log t. And the point here is that these two terms are lower order of magnitude compared to log d. That log d is clearly smaller order of magnitude than log d. But log t, of course, that's because in ansatz I'm saying that the right answer is when t is constant. So you have to sort of then verify that that's the right answer, but I just want to give you intuition. So take this for granted. Minus 1 minus t log d over d log 1 minus t log d over d, and finally minus d over 2 t squared log d over d, and that's the entire absolutely squared here, very good. And now let's simplify. So here we get this is equal to t log squared d over d. This is smaller order of magnitude. And here, what do we get? This is order 1, but this, when d goes to infinity, is order log d over d. Whereas the dominating term here is log squared d over d. So that this whole part is actually gone conveniently. Something that is nice when d is large. Yeah? Is that clear or no? I'm using really the first order Taylor expansion here, saying that log 1 minus z is approximately minus z when z is small. This is approximately 1. So this whole expression is approximately log d over d. But we have a larger order term here, log squared d over d. Okay, so we have this, and then the other surviving term is this minus 1/2 t squared log squared d over d. Nice. And everything else is little o of what we want. So now we have the same order of magnitude here and here, and we have t minus t squared over 2, which is conveniently greater or equal to 0 if and only if t is less than or equal to 2. Yeah? So we just proved, going back, we proved that the largest independence ratio is at most 2 log d over d. But in fact, it's also at least 2 log d over d. The proof of that requires the application of so-called second moment method. It's far more involved, although the types of computations that you have to do in the end is very similar. Any questions so far? Okay. Back to algorithms. Okay. So we know the truth is, we know that the independence ratio alpha d is approximately 2 log d over d. What about algorithms? Here's perhaps the most embarrassing story of this entire field. There is a simple algorithm, which is called greedy algorithm, which produces an independent set such that its asymptotics is half of what you want. So you can get half of the independent set that you want to produce. The algorithm is extremely simple. It's called greedy, but I think it's giving too much credit for it. It's really a stupid algorithm. This is how it works. You blindly pick a node in your graph. You put it in. You look at the neighbors. You kill them. And repeat. You never look at the degrees of the nodes. You never do any kind of a sophisticated optimization or any of that stuff. You just blindly create an independent set from this procedure. It gives you log d over d ratio, and any attempt to beat that threshold failed. Okay? And this is where we are, by the way. Nothing we know of actually beats that. But perhaps there is a polynomial time algorithm to beat that. There's not ruled out. But what is ruled out as of now is that local algorithms do not beat that threshold. The power of local algorithms, as far as this problem is concerned, is not stronger than just this naive, greedy algorithm. So let me formalize it as a theorem. For any rule f which produces independent set, and let's say denoted by I of f, the expected value of I of f normalized by n is asymptotically at most log d over d. And I hope you are fine with this asymptotic notation. Basically, it means take a sufficiently large d and take any rule which produces an independent set. That size, the relative size of the independent set, will be at most log d over d, plus a little epsilon here that I'm just ignoring. Any questions about that statement? Yes? Could you speak up a little? When you look at the constant size neighborhood for arbitrary constant and arbitrary rule. Well, you can push it a little bit. As far as you can push it, perhaps. I think the same proof applies if you push it to something like log depth. But if you're looking at the depth beyond log n, then you're pretty much looking at the entire graph, so that's no longer local algorithm. So you have to be careful at the depth. So it still has to be local algorithm, because if the algorithm is not local, then such rules trivially exist by. Okay? Any other questions? Yes? So to put it more properly, so for every epsilon, there exists a sufficiently large d0 that for all d bigger than d0, I might have to quantify, and for every rule f, that ratio will be at most 1 plus epsilon log d over d. Oh, this is the right order quantifies, but yes, and yeah, so for all f, lim, sup, and for arbitrary bounded depth. So okay, so this rule f encodes the depth as well. So that's why I didn't explicitly put it down. But the rule f applies to particular. So another perhaps a simpler way to think about it is as follows: you fix a rule. Maybe that's a better way. Fix a rule. That's your rule. Has arbitrary. You decide yourself what's the depth and what's the rule. You fix it. I can find large enough d such that what you produce is at most 1 plus epsilon log d over d. Or to be exact, fix a rule, fix epsilon, I can find large enough d such that you will not beat that threshold. I apologize for several asymptotics here, but that's the nature of the result. I'm not sure I can simplify it any further. Questions? Yes? Yes, it applies both. Erdős-Rényi and random deregulograms. And the proof is similar. Details are somewhat different because the... Okay, now, whatever... I don't have that much time left, 5-7 minutes, something like this. 5 minutes. Let me tell you the idea of the proof. And then we will wrap up. Okay, so stay here. The basis of the result, the basis of the theorem comes from establishing a very important structural properties of independent sets. And I won't give the full generality of that result, but more limited statement. So suppose, so fix any beta in the interval between 0 and 1, and fix any two independent sets I and j such that their cardinality is 1 plus beta log d over d times n. Right? Such independent sets exist because I fix my beta to be at most 1, and absolute bound here is 2, so such independent sets exist. Well, theorem, when beta is bigger than 1/2 plus 1/2 root 2, and that can be improved by you need to do more work, and that the statement that I'm about to give, strictly speaking, does not apply. You have to do more sophisticated thing. But at least for beta in this regime, there exist two numbers, tau 1 less than tau 2, such that if you look at the intersection of these two independent sets, normalized by the number of nodes, it's either less than tau 1 or it's bigger than tau 2 or it's bigger than tau 2. So what it means is that with high probability, for any pair of such independent sets. So what it means that take any two, in your graph, take any two independent sets, either they look together something like this, where they have intersection less than tau 1, or their intersection is quite significant, it is at least tau 2, but nothing in between is possible. In fact, now the question is, what are those values, tau 1, tau 2? You can actually show that this, as beta approaches 1, in other words, as you approach the largest independent set, tau 1, you can make it pretty close to 0, and tau 2, you can make it pretty close to size of the independent set. Converges to 2 log d over d. In other words, that picture, this tau 1 and tau 2, that separation becomes very extreme. Either they really have to overlap when they are close to optimality, or they barely overlap. And this gap actually widens as beta approaches 1. This is a theorem that requires a proof. The proof is based on a first moment method. Just like in the exercise before, what you look is that you look at the expected number of pairs of independent sets with intersection in tau 1, tau 2, and you show that this goes to 0. And that can be done almost the exact same way as we did this exercise, except for instead of one independent set, you look at the pairs of independent sets, and you say, look at the all possible choices, and look at what's the likelihood that these two sets are such that both of them are independent sets and have a particular intersection, and then you do some algebra, and that shows that goes to 0. And now the last thing that I wanted to mention is that why does this property creates an obstacle for existence of local algorithms? And the short answer is that if local algorithms existed, I would be able to create two independent sets with pretty much arbitrary level of intermediate intersection between them, and thus arrive at a contradiction. And this is how that works. Suppose such a rule exists, F, which creates independent set with relative size 1 plus beta log d over d. I'm going to skip n with your permission, just to keep things fast, and I'm already running out of time. That means that, okay, that means that if you apply the random seeds of your if you generate random seeds and apply this rule F, you create an independent set I, which has that size. By assumption, we're going to use the contradiction argument. Suppose that that was the case. Let's do it again. Yes? Mm-hmm. Yes? No, symmetric difference of y, because they can have edges. No? Yeah. Okay. So you create another independent set, J. If you look at their intersection, because their relative sizes are this, and the seeds are independent, the relative size is the square of this quantity. That's because you have to, in order to include a node into your independent set, you have to be successful twice. In the first experiment and the second experiment, so it's a square of this quantity, and one can verify that that quantity is strictly smaller than tau 1. Tau 1 happens to be larger than this. So you have tau 1, tau 2 here, and that. So you've created two independent sets which have intersections smaller than tau 1. There's no contradiction yet here because only this intersection, this range are impossible. But then what you do is that you look into independent sets created by intermediate random seeds. You start step by step interpolating between this random sequence and this random sequence, going one by one from the first to the second. So for the first term, first t nodes, you use the first seed. The remaining n minus t nodes, you use the second one. And what happens is that you start creating, so if the initial two independent sets were look like this is I, this is J. As you move from this sequence in this way, you start moving J towards I, step by step. And every time when you do this update, because the rule is local, you only impact a small neighborhood, constantly many, on average, nodes around this node where this switch was done. So you start moving in this direction. At some point, you will create an independent set with intermediate intersection which falls into this region. But we already proved separately that such two independent sets cannot possibly exist. That gives you a contradiction. And that's an argument. So unfortunately, local algorithms cannot beat the trivial threshold asymptotically. This approach can be extended to other models. some other models, and one model that I was hoping to talk about, but I don't have time, is random case satisfiability problem, where there's also a question of designing good algorithms for finding satisfying assignments. Offline, I'm happy to talk about this, but now I'm quite substantially over my time, so I'll stop. Thank you. Questions? Yes? Regardless of the random seeds, here's the think about the random regular graphs. That's where it's immediate, more immediate to see why such a rule cannot exist. In random regular graphs, all neighborhoods are identical. If you don't use randomization, if you don't use random seeds, then you have to produce the same answer for every node. If every answer is 0, it's an empty independent set. If every answer is 1, it's not an independent set, it's a full graph. Yes. Yes? Yes, so it would be hard to do brief. So first, one correction, it's not a k-set problem, what's called a not all equal k-set problem. So this is not a, so k-set problem is a Boolean constraint satisfaction problem where you have clauses and you have a conjunction of clauses, and every clause is some disjunction of variables and their negations, perhaps. You generate this formula uniformly at random. It's possible to show that in certain regimes that the formula has a satisfying assignment. The goal is to find an algorithm that finds such a satisfying assignment, and the gap where the satisfying assignment exists with high probability versus the algorithmic, what can be achieved by algorithm, is quite large. And it's almost the same story verbatim, except for here the gap was half, there the gap is 1/k in some appropriate modification of the formulation of the problem. But offline, again, I'm happy to give a more detailed description. Yes? Right, so this is, as I said, I skipped all the references, but the 1/2 plus 2√2, that's in my joint work with Madhusudan, and the improvement for all beta comes from the work of Raman and Dirac. And what they do is they consider, instead of 2 independent sets, they consider M independent sets for a carefully chosen M. They consider a certain overlap structure between them, prove some identity, and then prove that, in fact, if local algorithms exist, you would violate this identity, and so on. So the improvement comes from considering many as opposed. And that was actually instrumental also in our work for the k-set model. You also have to look at the several Boolean satisfying assignments. One. No, I think I should have put F in in front. So for every f and for every epsilon, there existed sufficiently large d such that above this, the independent set that you predict not uniform. That's right. Yeah, so somehow it should be. But whatever is the rule, it's yeah, right. So for every epsilon, there exists a large enough d such that above this and above. No, it looks then it looks right. First one, okay. Sequence of f's. Yeah, as long as the order of limits is correct, and yeah.